In the previous video, we discussed an example of hypothesis testing of proportion using the rejection region method. Recall, our null hypothesis was P is equal to P0, where P0 is equal to 0.45, versus its alternative hypothesis is P is larger than P0. And we also had other conditions like we observed the sample proportion is equal to 0.55, and we also had the sample size, which is 100, right? When we used the rejection region method, we first fixed the probability of making type 1 error as a small value. So the probability of making type 1 error, given the conditions that H0 is true, and we reject the null hypothesis, right? So this probability should be very small, and we fix this value to be a small value, say 5%. Okay, so let's say this is the corresponding probability, which is equal to 5%. Okay, and this interval is our rejection region. I'm going to use orange to represent the rejection region. Okay, and this is my critical value decided by the value of alpha. Okay, so what if your boss wants you to make your decisions based on different significance levels? Say if your boss wants to change your probability of making type 1 error from 5% to 10%, so which means the corresponding area, I'm going to use red, would be here. Okay, so this is say 10%. Okay, so you're going to have another critical value, C2, which means your final decision based on this critical value will be changed, right? Because the critical value has been changed. Or what if your boss wants your alpha to be equal to, say, 1%? Okay, so you're going to have its corresponding C3 here. Okay, so every time when you'd like to change the value of making probability of making type 1 error, your corresponding critical value will be changed, and then which means your decisions will be changed. Okay, so you started thinking, is there any way for us to make our decision easily? The answer is yes, and the method is called the p-value method. So this idea is to calculate the smallest value of alpha for which H0 can be rejected. So first of all, let's take a look at the definition of the method. Okay, it says p-value is the probability of finding the observed or more extreme results when the null hypothesis is true. So the first time when I saw this definition, I found it was pretty hard for me to understand. But I started thinking, okay, can I find some keywords to understand it deeply? So the first keyword of this definition is the probability. Okay, so p-value is the probability of something, which means p-value, first of all, is a probability. It should be between 0 and 1. Okay, what about the second keyword? The second keyword is it's this one. So finding the observed or more extreme results. Okay, so what does it mean? So the only information that we have is that we know that the observed sample proportion here is 0.55, and that's all we have. Okay, so we're going to make our decisions based on this information. So what we have observed here is p hat is equal to 0.55. And what about it goes more extreme? So here extreme means rarer. Okay, so in this case, because our alternative hypothesis is p is larger than p0, when you did the rejection region method, essentially you just need to find a rarer case, right? So when when p hat is larger than a critical value, so it goes to this way, right? It's a more extreme case. So in this p-value, it's pretty similar. In the p-value method, it's pretty similar. Okay, so more extreme means your p-hat is larger than this observed value, 0.55. So finding the observed or more extreme means p-hat is larger or equal to 0.55 when the null hypothesis is true. So you see the definition is constructed by three parts. First of all, p-value is a probability. Okay, so it's between 0 and 1. Second, the p-value method considers the sample proportion you have observed and goes to a rarer case. Okay, so here what you have observed is that p-hat is equal to 0.55. And if it goes to a rarer case, it means it's larger than this observed value. Okay, so larger or equal to this observed value under the assumption that the null hypothesis is true. So here, this curve means under the null hypothesis. Remember, so if your alternative hypothesis means p is larger than p0, so the curve will be like this. I'm going to use, say, pink. Okay, so this pink curve would be my alternative hypothesis. Okay, so if it's under the null hypothesis, it will be the black curve. And what's my p-value? Okay, as we all know that, because the distribution of p-hat approximately follows a normal distribution, it's a continuous distribution, so it's meaningless for us to calculate the probability of a single point, right? So a useful probability is to calculate the probability that my p-hat is within a specific region, that is to calculate the corresponding area under the curve h0. Okay, so what we have observed is p-hat is equal to 0.55. Okay, and so the probability that p-hat is larger or equal to 0.55 under the condition that HO is true is my p-value, right? So this would be my corresponding p-value, which is the corresponding area. Okay, so this green, blue area is my p-value. Okay, then I compare to a specific alpha. So we call alpha, in general, we say alpha is called significance level of a test. Okay, then you compare this blue area to this red area or black area or green area. It really depends on what kind of significance level you want to have. Say if you want your significance level to be 5%, that is alpha is equal to 5%. Okay, so you need to take care of the black area, right? So you need to compare the black area to the blue area and to see which one is bigger. Okay, if the blue one is bigger, which means you fail to reject the null hypothesis. If the black one is bigger, which means you reject the null hypothesis. Okay, so that's the basic idea of the p-value method. It's very commonly used in your daily research. Okay, so it's more popular comparing to the traditional rejection region method, because in this case you don't have to recalculate the critical values every time when you want to change the value of your alpha. Okay, you just need to calculate your p-value based on what you have observed. Okay, then you compare this p-value to the existing alpha. Say if you want your alpha to be equal to 10%, so you just need to calculate to compare the value of p-value to 10%. Okay, if your alpha is equal to 1%, then you just need to compare your p-value to 1%. So in this specific example, our null hypothesis is the population proportion is equal to 0.55. versus its alternative hypothesis is P is larger than 0.45. Okay, so the corresponding p-value is the probability under the null hypothesis is true. It means P is equal to P0 is equal to 0.45, right? And what we have observed is that P hat is equal to 0.55, okay? And if it goes more extreme, it means it's larger than 0.55, okay? So what we have observed, or more extreme, means larger or equal to 0.55. So this is my p-value, okay? And like what we did before, we'd like to convert this p hat to z distribution because we know that p hat approximately follows the normal distribution with p by n p by 1 minus p divided by n. Okay, so this is the distribution of p hat. We'd like to convert p hat to a z. So we're going to use p hat minus the expectation of p hat divided by the standard deviation of p hat is larger or equal to 0.55 minus the expectation divided by the standard deviation, given the condition that p is equal to 0.55. Okay, so this part is my z. So its z is larger or equal to 0.55 minus the expectation divided by the standard deviation, which is the square root of the variance. Okay, so which is equal to this. Okay, under the condition that p is equal to 0.55, so we have to plug in the value of p0, right, where p0 is equal to 0.55. Okay, so this is, now you have 0.55, you have the values of p0, you have n, so this is 2.01, okay, so which means the p-value is equal to 0.0222. You can check this using the z-table, okay, so therefore, for the test with level, say, alpha is equal to 5%, we will reject the null hypothesis because my p-value, 0.0222, is smaller than the stated alpha, which is equal to 0.05, right? So we reject the null hypothesis. Okay, so if your p-value is larger than alpha, let's say if this were not equal to 0.222, if it's equal to 0.6, let's just assume that, okay, for the sake of this problem. Say if it's 0.6, then it's larger than alpha, okay? So we fail to reject the null hypothesis, okay? But definitely here, it does not equal to this one, so we cannot have this conclusion, okay? So this is our final conclusion. Say if you would like to change the value of alpha, say if your alpha is equal to 0.1, okay, say this one is still smaller than 0.1, you still reject the null hypothesis, okay, but if you would like to change your alpha to a very small value, say 0.001, okay, so in this case your p-value is larger than this one, so you fail to reject the null hypothesis. So if you observe this p-value method, you're going to find essentially what we did was to compare this value. Okay, so this value can be written in this way. Right? You compare this value to z alpha. Right? So if this one is larger than z alpha, you're going to reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. So first of all, we have to write down z, so which is equal to this, right? So remember, this is the expectation under the null hypothesis, and the denominator is the standard deviation of p hat under the null hypothesis. Okay, so this is called this z is called the z statistic. Okay, so when your hypothesis is p is equal to p0 versus the alternative hypothesis is p is larger than p0, you will reject the null hypothesis when your z statistic is larger than z alpha. Okay, so once you fix your alpha, you're going to have a fixed z alpha using the z table. Okay, so this is the first case. The second case, so if your alternative hypothesis, you keep the same null hypothesis, and if your alternative hypothesis is p is smaller than p0, you will reject the null hypothesis when your z statistic is smaller than negative z alpha. Okay, so it would be like this. So this is your z curve. Okay, and this is your, say, negative z alpha here. Okay, and you compare your test statistic z to negative z alpha. If it's smaller than this value, you're going to reject the null hypothesis. So the last case, your alternative hypothesis is p is not equal to p0. So in this case, you reject the null hypothesis if your z is smaller than this value or z is larger than this value. Remember, we call this the two-tailed test. Okay, now let's just use this rule to figure out our first example. Okay, example 10.8. So in 2001, a National Vital Statistic report indicated that about 3% of all births produced twins. Data from a large city hospital found that only 11 sets of twins were born to 700 teenage girls. Does this provide strong evidence that the rate of twin births among very young mothers is less than 3%? So question A, define the parameter of interest and state the relevant hypothesis. So in this problem, first of all, we have to decide what kind of information do we have. Okay, so the report indicated that about 3% of all births produced twins. So as you can see, it's a problem with respect to the proportion. Okay, and the report in 2001 indicated that the proportion should be 3%. Then we have some data. Okay, so data from a large city hospital found that only 11 sets of twins were born to 700 teenage girls. Okay, so it means, so my data, of course, is a sample. Okay, so the sample is selected from 11 sets of twins were born to 700 teenage girls. Okay, so the proportion should be 11 divided by 700, right? So this should be my sample proportion. It shouldn't be the population proportion because it's drawn from the data. The statement that p is equal to 3%, and we'd like to figure out whether there is any strong evidence that the rate of twin births among very young mothers is less than this value. Okay, so versus p is smaller than 3%. Okay, so I will set this one as my null hypothesis, and this one as my alternative hypothesis. Okay, question B. Given a significance level alpha is equal to 5%, what's your conclusion? Give the procedures in detail and explain the conclusion in the context. Remember, a general procedure for a hypothesis testing should be, in the first step, set up your appropriate hypothesis, which has been done in question A. Okay, so in the second step, you need to figure out your test statistic. Okay, so in this case, we can just find the corresponding z statistic because your, the sample proportion, p hat, which is a random variable, approximately follows a normal distribution with expectation and variance, right? So my z should be p hat minus its expectation divided by this stuff. Okay, so under the null hypothesis, your P should be equal to P0 is equal to 0.03. So you need to plug in the value of P0. Okay, so Z approximately follows the standard normal distribution. So, and you can have the corresponding rejection region because our alternative hypothesis is P is smaller than P0. So you have this direction, okay? So this will be the one that you would like to have, okay? So you reject the null hypothesis if Z is smaller than negative Z alpha. So alpha is equal to 0.05. Once alpha is decided, so this critical value can be known from the Z table. Okay, then you calculate the observed Z statistic. So this one is equal to P hat, you plug in the value of P hat, right? For the rest of the arguments, say P0 or N, they are known, right? So P0 is 0.03, N is equal to 700, and this observed P hat is equal to 11 over 700. So everything is known. So this is equal to negative 2.22. Okay? So, like we discussed before, we reject the null hypothesis if my Z statistic is smaller than this value. Okay, so if alpha is equal to 0.05, you can have this value from the Z table. So this one, if you check the Z table, is equal to negative 1.65. So Z observed is equal to negative 2.22, smaller than this critical value. Okay, so which means you reject the null hypothesis and you support the alternative hypothesis. That is, there is strong evidence that the rate of twin births among very young mother is less than 3%. Okay, so that's for question B. So question C, describe the type 1 error and type 2 error in this context. Okay, question C. So first of all, remember what's your type 1 error? Type 1 error is a mistake, okay, when the null hypothesis is true, but you reject the null hypothesis. Okay, reject the null hypothesis when the null hypothesis is true. You reject the null hypothesis when null hypothesis is true means you reject H0, that P is equal to 0.3, while the actual rate of twin births is 3%. Okay, so what's type 2 error? So type 2 error is when your null hypothesis, when your null hypothesis is not true, but you fail to reject the null hypothesis, right? So you fail to reject H0 while the actual rate of twin births is less than 3%. Okay, so that's for question C. Okay, question D. Which error might have been made in reaching the conclusion in B? So our conclusion from B is to reject the null hypothesis and support the alternative hypothesis. Okay, because our decision is to reject the null hypothesis. So which kind of error can we make based on this decision? So of course is type 1 error, right? Because for type 1 error is when HO is true, but you reject HO. Okay, so question D, type 1 error. It cannot be type 2 error because type 2 error is to fail to reject the null hypothesis, right? But here we reject our null hypothesis, so it should be type 1 error. All right, so the last question, question E. If the actual rate of twin births is 2%, what is the power of this test? So recall the power of the test is the probability when H0 is false and you reject H0. Right? You reject H0 when H0 is false. So first of all, you will have to find when to reject H0 in this case. That is to find the rejection region. Okay? So the rejection region should be, like we discussed before, if we use Z, right? So Z should be smaller than negative Z alpha in this problem, is equal to negative 1.65 from the Z table. Okay? So this is equal to P hat minus P0 divided by P0, 1 minus P0 divided by N, okay, smaller than negative 1.65. So this P0 is 0.03, N is equal to 700, right? Okay, so this can be calculated as P hat is smaller than 0.019. Okay, so within the brackets is the rejection region. Now we have the rejection region, right? Then we can calculate the probability of reject the null hypothesis when the null hypothesis is false. That is the power of the test. Okay, so our null hypothesis is the rate of twin birth is 3%, but the truth is it should be 2%. Okay, so it means it's false. So the probability that the condition is the null hypothesis is false equivalently is to say the probability is 2%. Okay, and we reject the null hypothesis. So P hat is smaller than 0.019. It falls into the rejection region. Okay, so this is my power. Again, I'm going to transform P hat to Z. Okay, so it's equal to this. Smaller than 0.019 minus P divided by the same thing. So given that P is equal to 0.02, so I'm going to plug in the value of P here. Okay, and I also know the value of N, which is 700. So this is Z smaller than negative 0.19 if you calculate this part. Okay, is negative 0.19. And then this corresponding probability is equal to 0.4247 if you check the Z table. Okay, so in the previous examples, we always checked, this value. But here, given this probability, we check this value. But in this problem, this value is given, and you check this probability. Okay, it's equal to 0.4247.